Have you ever wondered what's happening inside your phone battery? Or how some metals get that super shiny, durable coating? Well, it all comes down to a field of science called electrochemistry. It's all about the relationship between electricity and chemical reactions. Today, we're going to make this whole topic super clear and simple. Let's jump right in.
So here's our game plan. We'll start with the one thing that makes all of this possible. Then we'll look at the simplest kind of reaction and build up to a trickier one. After that, we'll check out some real-world examples, clear up a really common point of confusion, and finally peek into the future of this amazing tech.
Okay, first things first. We need an on switch. You know electricity flows through metal wires, right? But how do you get it to flow through a chemical compound? Well, you need something that can carry the charge. And in chemistry, that something is ions that are free to move around. We call them mobile ions. This is the absolute key.
To really get why these mobile ions are so crucial, take a look at this setup. We've got a battery, a light bulb, and two electrodes stuck in a pile of solid table salt. Everything's connected, but, the bulb isn't lighting up. So, what's going on? The big clue here is that the salt is a solid.
And here is the aha moment. In that first beaker with the solid salt, the ions are all there, but they're locked up tight in a crystal lattice. They can't go anywhere. But look what happens when you either melt the salt or dissolve it in water. The ions break free. They can finally move. And because they can move, they can travel to the electrodes, complete the circuit, and boom, the bulb lights up. So the main takeaway is super simple. If you don't have mobile ions, you don't get a current. Period. Now, this whole process of using electricity to break down a compound, it has a name. It's called electrolysis. And the name actually tells you exactly what it does. Electro is for electricity, and lysis, that's just a fancy Greek word for splitting. So we are literally using electricity to split things.
And the device we use for this is called an electrolytic cell. It's got three key parts. You've got your power supply, like a battery, that gives the whole thing a push. Then you have the electrodes, which are just conductors that dip into our chemical soup. And finally, you have the electrolyte. That's our substance that has those all-important mobile ions we were just talking about.
Okay, you have two electrodes, the anode and the cathode, and you absolutely need to know what happens where. So here's a little cheat code for your brain. An-ox red cat. Just burn that into your memory. An-ox stands for anode is where oxidation happens. That's the loss of electrons. And red cat means reduction happens at the cathode. That's the gain of electrons. An-ox red cat. Trust me, it will save you so much trouble.
All right, let's put this into action. We're going to start with the easiest version there is, the electrolysis of a molten substance. Molten just means melted. This is the simple mode because there's only one compound in the pot, so there's no confusion, no competition.
And don't let that word molten scare you. It literally just means we've heated something up until it melts into a liquid. Think about a molten chocolate cake, right? It's hot, it's gooey, it's liquidy, but it's still just made of chocolate cake stuff. A molten ionic compound is exactly the same idea. Just the ions of that one substance, now hot and free to wiggle around.
Let's use molten sodium chloride, or table salt, as our example. Since it's molten, the only things floating around are positive sodium ions, which are our cations, and negative chloride ions, our anions. That's it. This makes figuring out what happens incredibly easy because there's no fight for the electrodes.
So it's a simple case of opposites attract. The negative chloride ions are drawn to the positive anode. There, they lose their extra electrons and become chlorine gas. Meanwhile, the positive sodium ions head over to the negative cathode, where they gain electrons and turn into pure liquid sodium. See, an ox red cat in action. And just like that, we've zapped table salt and split it right back into its original elements, sodium and chlorine.
Okay, that was easy mode. Ready to level up? Let's make things more interesting by adding a new player to the game, water. When we dissolve our salt in water instead of just melting it, well, things get a little more competitive.
Here's the twist. Water itself can break apart just a tiny little bit into positive hydrogen ions, H+, and negative hydroxide ions, OH-. So now, instead of just having sodium and chloride ions, we have 4 different ions all swimming around. And this means we've got a competition on our hands at each electrode.
So this is the new scene.
over at the negative cathode, both the positive sodium and hydrogen ions are showing up, wanting to react. And at the positive anode, you've got both negative chloride and hydroxide ions crowded around. But here's the rule. Only one type of ion can win at each electrode. Only one gets to be discharged, which just means it reacts and loses its charge. This is a huge concept called selective discharge. So, how do we pick the winner?
We figure it out using this, the reactivity series. Think of this as the official rule book. It's basically a list that ranks how much energy it takes to turn an ion back into an atom. For the positive ions, the ones way up top like sodium, are super reactive. That means they love being ions and it takes a ton of energy to change them back. The ones lower down, like copper or hydrogen, are less reactive and way easier to change. So the simple rule is, the ion that's lower on the list wins. It's the path of least resistance for the electricity.
All right, enough theory. Why does any of this actually matter? Well, electrolysis isn't just some neat lab experiment. It's a massive industrial process that we rely on to make and purify the stuff we use every single day.
Two gigantic uses are purifying metals and plating them. You see the copper wiring on the left? That has to be unbelievably pure to conduct electricity well. We get it that pure using electrolysis. And on the right, electroplating. You know that shiny chrome bumper on a car or a silver spoon that isn't solid silver? That's probably just a cheaper metal underneath with a super thin layer of another metal plated on top, using this exact process to make it look great and stop it from rusting.
Now, we need to pause and make a really important distinction here, because this trips a lot of people up. So far, we've only talked about electrolytic cells. That's where we use electricity to force a chemical reaction to happen. But you can also do the complete opposite. You can use a chemical reaction to create electricity, and those are called simple cells. This table breaks down the differences perfectly. An electrolytic cell consumes power. It needs a battery to work. Its job is to turn electrical energy into chemical energy. But a simple cell is the battery. A chemical reaction inside it produces power, turning chemical energy into electrical energy. They are exact opposites. And look very closely. The polarity of the electrodes also flips. The anode is positive in one and negative in the other. That is a critical difference.
And the perfect classic example of a simple cell is the lemon battery. I bet you've seen one of these, maybe even made one. The lemon juice acts as the electrolyte, and when you stick two different metals in, they react with the acid. That chemical reaction happens all by itself and produces a flow of electrons. It creates its own electricity, enough to light that tiny bowl.
So let's wrap this up by looking forward. Because understanding this stuff isn't just about chemistry class. It's about understanding the technology that is literally going to power our future, from way better batteries to much cleaner forms of energy.
And this science is right at the heart of some incredible new tech. Think about hydrogen-powered cars. They run on fuel cells, which are really just very advanced, simple cells. Inside that cell, hydrogen and oxygen react chemically to produce electricity, and that electricity powers the car. And the best part? The only thing that comes out of the tailpipe is pure water. That's electrochemistry pointing the way to a cleaner future. So, at the end of the day, electrochemistry is a two-way street. We can use electricity to make stuff, or we can use stuff to make electricity. It's a fundamental power we have to control matter and energy. And that leaves us with a big question, right? Now that you know the rules of the game, what comes next? What huge problems in energy, materials, or even medicine could you solve by mastering this process? The potential is truly shocking.